This is Lesson 28 in our Calculus 3 series, Spherical Coordinates. So far, we've seen two different ways to describe points in three-dimensional space. We have our rectangular coordinate system. We also learned about cylindrical coordinates. Now we have spherical coordinates. So this is a different way to describe a point in three-dimensional space. We said that cylindrical coordinates was one natural extension of polar coordinates into three-dimensional space, and this is another one. Notice here that instead of having r, the radius, in the two-dimensional plane, now we have rho, the radius, in three-dimensional space. It's the distance from your point in space to the origin. But unlike the radius in polar coordinates, we're going to restrict here to rho greater than or equal to 0. We have theta, which is the same theta we have in polar coordinates. It's the angle made from the positive x-axis. And now we have phi, the azimuthal angle. That's the angle from the positive z-axis. And phi is going to go from 0 to pi only. Now let's examine these coordinates more closely and talk about some basic surfaces in spherical coordinates. What would happen if we set rho to be a constant? Rho is the distance to the origin. If rho is constant, we're talking about all the points that are equidistant to the origin. That's going to give us a sphere. Rho being constant gives us a sphere. Let's talk about theta being constant. Theta is the angle from the positive x-axis. Theta is this angle here. When we talk about the equation theta equals a constant, we're saying that rho could take on any of its values and phi could take on any of its values. Remember that rho is greater than or equal to 0 and phi goes from 0 to pi. So if we fix this constant theta, let rho take on any value, and phi go from 0 to pi, any of its values, we're going to get a half a plane. Now keep in mind that with cylindrical coordinates, if we have theta equals a constant, we get the entire plane, because in polar coordinates r can also be negative. But here our radius rho is greater than or equal to 0. And now what if we set phi to be constant? If phi is constant less than pi over 2, we'll have an upward facing cone. If phi is equal to pi over 2, we'll have the xy plane. And if phi is greater than pi over 2 and still less than pi, we have a downward facing cone. So it's important to keep these shapes in mind as we think about our triple integrals, because these are the shapes that we get by setting our spherical coordinates equal to constants. Now let's talk about converting between rectangular, spherical, and cylindrical coordinates. Here we have our point in three-dimensional space. We could call this point by its x, y, and z coordinates, or by its r, theta, and z coordinates, that was cylindrical, and now by its spherical coordinates, rho, theta, and phi. So let's see how all of these coordinates relate. Well, we already know how the x and y coordinates relate to r and theta. That's polar coordinate conversion, and we're pretty comfortable with that by now. But let's talk about how both rectangular and cylindrical coordinates relate to spherical coordinates. If this is our point rho, theta, phi, by taking a shadow in the two-dimensional plane, we can see that this distance is r. And this is the same distance we have up here, r. And so we can see that r is equal to rho sine phi. R is equal to rho sine phi. Also, from the same triangle, we can see that z is equal to rho cosine phi. So here we have relationships between cylindrical coordinates and spherical coordinates. Let's take this a little bit further and go to rectangular coordinates. If r is equal to rho sine phi and x is equal to r cosine theta, then x is equal to rho sine phi cosine theta. And y is equal to rho sine phi sine theta. And so now we have expressions for x and y in terms of spherical coordinates. And so actually we have x, y, and z now in terms of spherical coordinates. And again, the theta is the same between spherical and cylindrical, so here we have r and z, which we have in cylindrical coordinates, in terms of spherical coordinates. And notice because r is the distance from the point to the origin, we have r being radical x squared plus y squared plus z squared, or we can write that as radical r squared plus z squared in cylindrical. Now when we think about our volumes in spherical coordinates, we need to think about how we would break up a volume for the Riemann sums in our triple integral. So with spherical coordinates, we're going to be looking at the volume of these spherical wedges. So let's take a look at the spherical wedge we have here. We're talking about the wedge for which the angle phi is phi sub k, the distance rho is rho sub I, and the angle theta is theta sub j. So that the difference in rho values is delta rho I, the difference in phi values is delta phi k, and the difference in theta values is delta theta j. And with that, we're looking for the volume of this spherical wedge. So we're going to approximate its volume as if it was a rectangular box. So that means we need the dimensions of each side. Let's take a look at this red side first. We said that this distance is rho I, and this angle is delta phi k. So we've got a circular arc of radius rho I and of angle delta phi k. Our arc length formula, S equals r theta, gives us the length of this arc to be rho I delta phi k. Similarly, our purple side here is another circular arc, but its radius is coming from here, and that distance is rho I sine phi k. And this angle is delta theta j. So this circular arc measures rho I sine phi k delta theta j. And the green side here, we already said was delta rho I. So approximating this volume as if it was a rectangular box, we would multiply the dimensions of these sides, and we get rho I squared sine phi k delta rho I delta theta j delta phi k. And so for our triple integral in spherical coordinates, our dv, our volume element, becomes rho squared sine phi d rho d theta d phi. So let's take a look at how we can use that. Find the center of mass of a hemisphere of radius 2 with density proportional to distance from the origin squared. Okay, we're looking for center of mass, and we've got a hemisphere here. So we'll take it to be the top hemisphere. That'll be easier to work with. And based on symmetry, we're going to guess that x bar and y bar are equal to 0. But let's talk a little bit more about that. It's not just the symmetry of the region that's important. It's the symmetry of the density function on this region. We can see that this region is symmetric in x and y, but notice also that the density function is also symmetric in x and y. Because of that, and because we're centered at x equals 0, y equals 0, we're expecting the center of mass to have x coordinate and y coordinate equal to 0. So the real job here is to figure out what's the z coordinate of the center of mass. Well, we know the formula is 1 over mass of d multiplied by the triple integral over the domain d of z times the density function. And the mass computation is that triple integral over d of just the density function. Now, because our domain is a hemisphere, it's going to be easiest to describe this domain in spherical coordinates. So let's think about this entire computation in spherical coordinates. The density is proportional to the distance from the origin squared. Well, distance from the origin is rho. So density is proportional to rho squared. So density is proportional to rho squared. And we said that dv is rho square sine phi d rho d theta d phi. So looking at the mass computation, we've got the integral of the density function of k rho squared, and then dv is rho square sine phi d rho d theta d phi. Now what are the bounds on rho, theta, and phi? Well, for our domain here, rho, the distance to the origin, goes from 0 to 2. Theta, the theta angle, goes from 0 to 2 pi. And phi, the angle from the positive z-axis, goes from 0 to pi over 2. So our mass integral looks like this. And combining here, we have rho to the fourth, right? We have k rho to the fourth. And integrating is going to give us rho to the fifth over 5 times k sine phi. Plugging in our bounds gives us 32/5 k sine phi. Integrating this on theta just makes this all a constant times theta. Plugging in those bounds, 64 pi k over 5 times sine phi. And integrating on phi, we get 64 pi k over 5 as the mass of our hemisphere. So now we want to integrate z multiplied by the density over our domain and have 1 over the mass here, right? That's the formula for z bar. So 1 over the mass, we have 5 over 64 pi k. The bounds are the same because we're describing the same domain. So we have rho going from 0 to 2, theta going from 0 to 2 pi, and phi going from 0 to pi over 2. The conversion from rectangular to spherical coordinates has z equals rho cosine phi. So that's rho cosine phi here. Our density function, we said, is k times rho squared. And our volume element is rho square sine phi d rho d theta d phi. So simplifying and integrating, we're here. We can cancel our k's. Even from the very start, we can cancel our k's. When we plug in the 2 and get a 64, we can cancel our 64's here. And then integrating on theta and plugging in 2 pi gives us a pi that'll cancel. So we end up with 5/3 integral 0 to pi over 2 cosine phi sine phi d phi. This is a nice u sub. U is equal to sine phi, so du is cosine phi d phi. So we have integral of u, and our bounds become 0 and 1. And so we get 5/6 to be z bar. So that's the z-coordinate of our center of mass of the hemisphere. Let's take a look at another example. We want to find the volume of the part of the solid of the spherical ball of radius 1 with x negative, y positive, and z negative. So we're talking about the sphere of radius 1, but we only want the part with x negative. Here's our x-axis, so x negative is back here, y positive is here, and z negative. So this is the part of the solid ball we're talking about. Now because this is part of a sphere, we want to use spherical coordinates to describe our domain. So rho is going from 0 to 1. This is the sphere of radius 1. Theta is going from pi over 2 to pi, right? Theta is going around this way. So this is theta equals pi over 2, and this is theta equals pi. And phi goes from pi over 2 to pi. Phi is coming from the positive z-axis. So here we have phi is equal to pi over 2. And here we have phi is equal to pi. And so our triple integral for volume looks like this. Remember that this is the volume element. This is dv, rho square sine phi d rho d theta d phi. So rho goes from 0 to 1, theta from pi over 2 to pi, phi from pi over 2 to pi. So the integration is pretty simple here. And we get pi over 6. Now if you remember the formula for the volume of a sphere, 4/3 pi r cubed, what we found was 1/8 of the volume of the sphere of radius 1. So that gives us the same answer of pi over 6. Now you might be wondering at this point, how do you know which coordinate system to use when you're setting up your triple integral? And what I want you to look out for with spherical coordinates is a domain that is a sphere or part of a sphere. Now, when your domain is a sphere or part of a sphere, your domain will be most easily represented in terms of spherical coordinates. So that means the bounds on your integral are going to be the simplest. They'll all be constant bounds in spherical coordinates, which is great. However, sometimes the function inside your integral is not going to be so nice in spherical coordinates. So we can't say that anytime you're integrating over a sphere to use spherical coordinates, but we say consider using spherical coordinates anytime your domain is a sphere. So let's take a look at an example where we can compare the spherical coordinates with cylindrical coordinates and see the differences in the triple integrals. So for example, find the triple integral over d of x squared plus y squared, where d is a solid below the sphere x squared plus y squared plus z squared equals 4, and above the cone z equals radical x squared plus y squared. So this is the solid that we're talking about. And because we have part of a sphere, we're thinking spherical coordinates. And let's describe this domain in spherical coordinates. This is a sphere of radius 2. So rho, the distance from the points to the origin, is going to go from 0 to 2. Theta is going to go 0 to 2 pi, and phi is going from 0 to pi over 4. Now let's see how we get this phi equals pi over 4 bound. One way you might recognize it is to see that for z equals radical x squared plus y squared, we get traces when x is equal to 0. We get z equals radical y squared, so that's absolute value of y. And when y equals 0, we get z equals absolute value of x. And so the absolute value function we know has slope 1 and angle 45 degrees. So that would tell us that we're going to pi over 4. But if you don't recognize that, we can just go back to the formulas, and that always works. So here are our conversion formulas for x, y, and z in terms of rho, theta, and phi. Z equals square root of x squared plus y squared says that z squared is equal to x squared plus y squared. So we'll take z squared, set it equal to x squared plus y squared, and here I'm factoring out the common factor of rho squared sine squared phi. So the cosine square theta plus sine square theta, that's equal to 1. And we can divide by rho squared on both sides. So we get cosine square phi equals sine square phi. Or tan square phi is equal to 1 if we divide both sides by cosine square phi. This tells us tan phi would be positive or negative 1. Now we know that phi is between 0 and pi, so which values for phi would give us a tan value of positive or negative 1? Well, we'd get a positive 1 at pi over 4 and a negative 1 at 3 pi over 4. But we also know that z is a positive radical here, so z must be greater than or equal to 0. Z is equal to rho cosine phi. Rho is always greater than or equal to 0, so that tells us that cosine phi must be also greater than or equal to 0. So which of these values has cosine positive? It's the pi over 4. So phi is equal to pi over 4 for the cone. So now we're ready to integrate in spherical coordinates, and we also need to take a look at our inside function, x squared plus y squared. In spherical coordinates, x squared plus y squared is equal to rho squared sine square phi. So that goes here, our rho squared sine square phi. Then we have our dv, rho squared sine phi d rho d theta d phi. And when you carry through this integration, you're going to get integral of sine to the third phi d phi. Now going back to Calc 2, we remember that we have to separate this into sine phi, sine square phi, replace the sine square phi with 1 minus cosine square phi, then distribute the sine, and then continue to integrate. So notice that in spherical coordinates, the domain was described very simply, right? All the bounds are constant here, but the inside function is not so simple to integrate. It requires a bit of work. So we might consider instead cylindrical coordinates here. And let's take a look at that. In cylindrical coordinates, our inside function is x squared plus y squared, so that's equal to r squared. Our top surface is z equals radical 4 minus r squared. Our bottom surface, the cone, is z equals r. So far, we have r squared as our inside function. We have r dz dr d theta as our volume element dv for cylindrical coordinates. And we have our bounds on z. Now to find our bounds on r and theta, we need to consider the domain in R2. So what we need is the curve of intersection here, because that's going to define for us the domain in R2 over which we integrate. So setting the equations for the sphere and the cone equal, I've got z squared here is equal to z squared here, gives us r squared is equal to 2, and so we know that r goes from 0 to square root of 2. And with that, theta goes from 0 to 2 pi. So those are the bounds on our integral in cylindrical coordinates. Notice they're not quite as simple as the bounds we had in spherical. However, when we do the integration here, the integration is going to be a bit more simple, because when you integrate on z and plug in these bounds, you can solve with a u sub. And most students are more comfortable with u substitution than they are with powers of sines and cosines. So I'm just saying that we can't guarantee that every integral you have over a spherical domain is going to be simpler in spherical coordinates. However, when you have a spherical domain, you should consider using spherical coordinates because it may be simpler. In either case, our integral turns out to be negative 16 pi over 15 times 5 radical 2 minus 8. And with this, we'll conclude our lesson on spherical coordinates.